In this lesson, we will focus on precisely describing the specific requirements of a manufactured product, and to do it in such a way that the information is useful for choosing the material. We've already mentioned that choosing the best material happens when we're able to harmoniously combine the design requirements of a given product with the property profile of a material. For this reason, the first important step in our selection process will be to provide a clear description of the design requirements and to do so in terms of material properties, so as to make it easier to compare all possible candidates. The approach we will describe in this lesson refers to the design strategy outlined by Professor Ashby and adapted to various design fields in his textbooks, which we highly recommend to anyone who wants to become an expert in the material selection process, or in any case, to anyone who wants to learn how to manage material data in a project. According to this approach, design is seen as a process that starts from a market need or an innovative idea and ends with the description of the product specifications. It can involve a new project when we want to develop a new product, or it can be a redesign when we want to improve certain features or performance of an existing product, or it can correct its behavior in use. Anyways, the drive to design can arise from very different needs. For example, it may come from the desire to gain greater competitiveness in the market, to make functional improvements to a product, to promote innovation in the sector, to reduce the environmental impact, size or weight, or to improve a product from a safety perspective. Lastly, it's important to clarify that the end point of this process is not the actual product itself, but rather the so-called product specifications, a set of useful information to make it a reality. The process followed in design is divided into several phases, which we will now look at in detail. The first step is the idea of the product. This is a predominantly conceptual phase where various shapes for the product and different operating principles are considered and evaluated. The most promising ideas are translated into a concrete form in the second phase, which we call the modeling or model phase. Here, preliminary drawings of the product are made, sketching out its shapes and dimensions. Possible materials and manufacturing processes are selected, also taking into account factors such as performance or costs. Finally, the last step concerns detailed design, where everything is defined precisely: dimensions, materials, shapes, and the most suitable production method. This leads to the complete specification of the product, which will be evaluated and, if approved, will move on to the stages of creating a real prototype of the actual product. If, on the other hand, the result is still not entirely convincing, the process continues iteratively by revising one or all of the previous design phases. As an example, let's try to outline the designing steps for the folding bicycle. The initial requirement for this project can be identified as the idea of designing a compact and lightweight vehicle, easy to transport and store, and suitable for short daily trips, especially considering the increase in city traffic and the growing interest in sustainable mobility. The ideation phase will consider how the various types of assembly methods can allow for a bicycle that, when folded, is compact enough, and to have a folding system that is simple and quick. In the modeling phase, to concretely translate the idea, drafts, drawings, and CAD models are created to highlight the various aspects of the product. At this stage, possible materials and processes for making the product are also proposed. Subsequently, in the detailing phase, the focus will be on sizing the individual components to keep the weight down and to ensure a rigid and sturdy structure for the safety of the bicycle. Finally, the quality of the product will be verified through evaluation by other experts or by creating a prototype, assessing its stability, ease of folding, and riding comfort. Possible iterative cycles of the idea could involve reinforcing the hinges or simplifying the folding mechanism. The process of selecting materials develops in parallel with the design process, providing the designer with increasingly precise and detailed data. In particular, during the ideation phase, the goal is to explore various solutions, keeping multiple design options open. Designers often need only rough property values covering a broad range of materials. Usually, a material family is then identified as most suitable. When moving on to the modeling phase, the selection becomes more targeted. The focus narrows to a specific class of materials whose properties will be described with a higher level of precision and detail. Finally, in the detailed phase, the project is refined even further. Extremely precise data is needed, relating to one or just a few materials, ready to be translated into real and reliable solutions, and into a correct sizing of the structure and its components. At this point, we've seen how to guide the design process in transforming an abstract idea into a concrete and detailed product. However, we still haven't discussed how to choose the material, or rather, how to match the project requirements to the ideal property profile. Here too, Professor Ashby's strategic approach comes to our aid, outlining the steps for correctly selecting the material. Material selection also takes place as a multi-phase process. In the first and fundamental step, we deal with the schematization or translation of the project attributes. In this phase, we transform the requirements of the product into a set of useful information for material selection. This step involves clarifying, for a given artifact, what are its functions, what are the constraints, the objectives of the project, and the free variables available to the project designer. We will then clarify, in the following slides, the meaning of these for items. The second step is a preliminary selection phase, a so-called filtering or screening phase, in which, among all possible candidates, those that are not able to meet the project requirements are eliminated. The established constraints thus become filters used to discard unsuitable materials. This step is followed by the classification or ranking phase, where we sort the materials based on their ability to meet a requirement of excellence, such as minimizing mass or minimizing costs. This phase, instead, specifically refers to the objectives of the project. The final task is to thoroughly explore the candidates that have proven to be the most promising. This is done by examining their characteristics in detail, such as typical uses, possible faults that may occur, and technical details related to their production or use. This last phase is also known as the documentation phase. We'll leave these last three operational phases for another lesson, while, in this one, we'll focus on the first step, which is translating the project. As we were saying, translating the project means analyzing the product and specifying its function. How will it operate, which constraints to be respected, which final objectives to pursue, and the free variables, which are the aspects where the project designer can choose the best material. Inspired by Professor Ashby's approach, let's try to write down the questions to ask in order to effectively translate the project. First of all, the function of the component must be specified, and to do this, we need to answer the question, what is the component used for? Possible answers could be to support loads, to withstand internal pressure, to act as a lever, to function as a spring, or as a thermal insulator. Next, we'll need to specify the constraints of the project, so answer to the question, what conditions must the material meet? The answer can be multifaceted. It may concern characteristics of the material, such as its stiffness, strength, whether it acts as an insulator or a conductor, whether it is transparent or opaque, or features related to cost or recyclability. These types of constraints are called functional constraints. Other types of constraints that we may encounter in design, on the other hand, concern the shape and dimensions established for a given product. In this case, we refer to them as geometric constraints. Finally, it's important to clarify that not all constraints carry the same weight. Some are absolutely non-negotiable, while with others, we can afford to be more flexible. Moving forward, it's important to clarify what the objectives of a project are, and to do this we can answer the question, which characteristics of the product do we want to maximize or minimize? For example, in a project we might want to minimize the mass of the product, its costs, its size, or its environmental footprint. Or perhaps we might want to maximize its stiffness, thermal exchange, or stored energy. The material that allows us to maximize or minimize one of these characteristics will be considered the best. And it is precisely based on these objectives that we can draw up a ranking of the material's performance. Finally, we ask ourselves which parameters the designer can change to optimize the objective. These will primarily concern the material and, where possible, the dimensions of the product that are not subject to constraints. These parameters are defined as free variables. But to clarify these points better, let's look, by way of example, at how the design requirements of two products are translated. For example, let's consider the case of a car bumper. Its main function is to effectively absorb the energy generated by collisions, thereby protecting the structure of the vehicle. Let's move on to the analysis of the constraints. The material used must ensure good absorption of impact energy and have good resistance to impacts. It must function properly over a wide temperature range, roughly from -40 to 80 degrees Celsius. Other important constraints include the recyclability of the material, resistance to weathering, and compliance with specific dimensions such as width, height, and shape. In some cases, paintability can also be essential for both aesthetic and functional reasons. The main design objective is to minimize weight. The free variables that the designer can adjust to optimize the objectives are the choice of material and the thickness of the component. As a second example, let's consider the case of a tennis racket frame intended for the mass market and for non-competitive or professional use. Although its shape can be complex, the function of a tennis racket frame is comparable to that of a beam subjected to bending, which transfers the player's energy to the ball and ensures precision and control in the shot. Let's identify the constraints. The racket must provide flexural and torsional stiffness, mechanical strength, fatigue resistance, and must withstand frequent impacts during play. The weight must be kept low so as not to tire the athlete, and the frame must withstand exposure to the elements. Another important constraint is the ability to dampen vibrations, the so-called damping. Finally, we assume that the shapes and dimensions are predetermined, as is usually the case for manufacturers and according to sports regulations. Given the target market, the goal in this type of project is to minimize cost in order to offer a competitively priced product, but without compromising performance. Finally, the free variables are identified, which in this case, since the geometry is already set, will concern only the choice of material. These two project translations can be valid for most bumpers and tennis racket frames. However, it's important to clarify that the choice of parameters, such as constraints, objectives, and free variables, is entirely arbitrary and depends on the designer's creativity or experience. In fact, it's precisely thanks to these parameters that it's possible to give a product its own distinctiveness or even uniqueness in the market. A good project designer, a designer, an experienced engineer, they know how to answer these questions or are able to change their answers if the product specifications don't meet expectations. In this lesson, we looked at the first step in material selection, namely translating the project, highlighting that choosing the material is a multi-stage process that aligns with the main phases of the project design: idea, model, details. The first step is to clearly describe the project requirements. The most suitable material will be the one whose property profile best matches these requirements. To effectively define the project requirements, the strategy suggested in Professor Ashby's approach is to outline the response in terms of function, constraints, objectives, and free variables. Once the project requirements have been defined or translated, we move on to the filtering and classification phases for the materials. Then comes the documentation phase, which supports the project's feasibility, as we will see in an upcoming lesson.